to show you now is called chromatography, and this is an experiment that you can try yourself at home, and I would really encourage you to do this. So what we have here is a piece of chromatography paper. You could use any sort of filter paper you have at home, and even like coffee filter paper should work okay. And this is chromatography paper, and what we're going to use it to do is separate soluble substances within a mixture, and in particular the dyes in ink, and we're just going to simply use some felt tip pens. So how we do this process is we've got our piece of chromatography paper, and what we want to do is we want to draw our baseline first of all. Now I'm doing this upside down because this is the bottom for you. So a couple of centimeters from the bottom we want to draw our baseline, so I'll just maybe do that at about 1.5 centimeters or so. It just needs to be a little bit off the bottom. And we do this, we draw this baseline in pencil. That's really important because if I was to do it in pen has ink in it which will dissolve in the water. The water we are using is our solvent, and so we don't want our baseline to dissolve in the solvent. We don't want that to pass up our chromatography paper. In chromatography paper, the paper is called our stationary phase. We have two phases. We have our stationary phase and we have our mobile phase, and that's the water, because the water will pass up the chromatography paper when we have these set up. Now, I'm going to put multiple spots on the same baseline, and we can do that. So I'm going just going to put a couple of X's in pencils to keep myself right of where to put them. And I also then want to write my original colours. So I'm going to use yellow, and what I'm going to do is put just a small spot here. I'll let that dry and put another wee spot there just to make that nice and concentrated, and then I'll put maybe one more spot. Now if you had a solution of a dye, you would use what we would call a capillary tube, and that would be where you drop a little bit of the solution and again spot it on these little X's. So next colour is blue. Quite a strong colour, so I'll maybe just leave that at 2 spots. Next colour I'm going to use is green. Okay, and the next colour I'm going to use is black. So what I'm going to do is I am going to put this in the solvent of water. So we need to choose a solvent where our substances are soluble in it, because if we choose a different solvent where they don't dissolve, our spots will simply stay on the baseline. I'm just going to turn this round, and what I'm going to do is just put the starting letter of each colour, just so that I know what colour they were to start with, so that if they separate out and I'm not sure what the original colour is or was, then I can check what the code at the bottom. So what I want to do now is put this into a beaker, and the beaker must contain my solvent. Now your solvent level must be below the level of your baseline. So I'm just going to put a little bit in, and we may need to add a wee bit more, but what you're doing is you're judging, are those spots going to be above the water level, because we don't want them to go into the water, otherwise they'll just dissolve in the water, and what we want is the water to actually travel past the spots and bring the water up with them. Okay, what I'm going to do to hang this into my beaker is I'm going to wrap it round a pencil. So I may need a little bit more water in here just as I do that. So we'll check that that hangs, and you can see at the minute if I place that on my beaker, it's not actually, the water level must be at the bottom of the paper so it can be drawn up by the paper, so I need a little bit more. Perfect. So you can see now, turn that round carefully so that it's not splashing up past my spots. Just going to draw this back a wee bit. We can see now that this is at a good level, My paper's quite high in the beaker, so that's why I've had to put quite a bit of solvent. Quite often you don't have to put this amount of solvent. But you can see that my chromatography paper is dipped into the water, but the water must not start above the baseline, otherwise the spots will just go into the water. So what we want is the water to rise up the chromatography paper, which you can see it is doing now. Again, just a wee recap of that term, the water is the mobile phase, so it is moving, and it's moving up past the stationary phase, which is our paper. And as it passes the spots are soluble in the solvent, so they will start to dissolve. And you'll see that these will rise up our piece of chromatography paper. And essentially what will happen is that if these inks contain more than one dye, they will separate out into the different dyes depending on how soluble they are in the water. The more soluble they are in the water, the higher they will travel on the piece of chromatography paper. So what we'll do now is we'll pause this and change it to a time lapse so that you can see this happen a wee bit quicker, and then we'll have a look at our final results. So you can see now our dyes have separated out in our different inks. You can see, I'll show you a close up in a wee second, that our yellow and blue have separated just into one colour, one spot as such. I know the blue's a wee bit of a streak, but there's not two different spots. So that tells us that the yellow and the blue are pure substances. And you can see the green has separated out into yellow and blue, and so therefore it's not a pure substance, it's made up of a mixture of dyes. And the black, you can see, are a number of different colours. And so what I'll do is I'll show you a dried in version of our chromatography paper, and you can see the different colours that black is made up of. So what we have here is the final chromatogram. That's the name for the term of the paper after it has been removed from your chromatography experiment and has been left to dry. We actually ran it again just to get a slightly better chromatogram that was a little bit less streaky, but with the same colours of pens. So a couple of things that we need to mention here. First of all, you can see that there's an extra pencil line on the chromatogram now, and that is what we call the solvent front. When your solvent is near the top of the chromatography paper, it's important to remove it from your solvent to prevent more water or solvent from being drawn up, because otherwise the spots can essentially run off the top of the chromatogram. And what we want to do after this is analyse it. So when it's near the top, you take it out and you mark the level that the solvent has got to in pencil, and then you let it dry. So that is the level that the solvent got to, and we call that the solvent front. And that will be important in calculating RF values, which allows us to analyse this chromatogram. So the solvent front is at the top, the baseline is at the bottom, and remember it's important that we draw both of these in pencil because we know that the ink in pen is soluble and would be separated out by the solvent, by the water in this case. So a couple of general things to point out first of all, and that is that our yellow and blue have turned out to be pure substances. And the reason we can tell that is that because on the chromatogram they have produced a single spot. They haven't separated out into multiple colours. They have produced a single spot. You can see they have travelled reasonably similar distances up the chromatography paper, which means they have a similar solubility in the solvent. But if we have a look at where the yellow is most concentrated, hopefully you can see where I've drawn over that there. When we take our RF values, which I'll talk about in a second, we take it at the centre of the spot. So it would be about there. So if I sort of colour that in, that's where our yellow would be most condensed. and the centre of the spot would be there. Now, if you're given a chromatogram in an exam, it's much more clear. The spots are much more perfect circles rather than what we've got here. But this is in reality what we would get from using pens in this sort of experiment. You can see the blue is slightly more condensed up here. So if I shade that in here and put a spot in the centre, you can see that the blue spot has travelled a little bit further, which means that blue has a slightly higher solubility in water. So let's now look at green. We can see that the green ink has separated into two spots. It's separated into a blue spot and a yellow spot. So if I draw that here, there's our blue and there is our yellow. And what you should notice is that these have travelled the same distance as our pure blue and yellow spots. So green is made up of blue and yellow ink. If spots have travelled the same distance, that will give them what we call the same RF value, and individual dyes will have the same RF value in a particular solvent. So you can see if we work out the RF value in just a minute for the yellow and for the blue, you'll see that they are the same. So you can tell that green contains blue and yellow dyes. And yes, we can obviously tell that from the colour, but if we had a black and white version of this, we would still be able to tell that it contains yellow and blue because it is at the same level as those pure inks. Let's have a look at black. Now you can see the blue has gone a wee bit higher in this. You can see actually, you might be able to see a very, very faint line. Obviously this paper had curved a little bit, and you can see a very faint line sort of up like this. So what that means is that the chromatography paper wasn't quite straight or quite level in the water, and so it's been drawn up a little bit more on the right hand side, so that's why the black has travelled a wee bit further. But if we just look for sake of colours and what it's made up of, you can see that there is a blue spot there, kind of purpley here, orange here, and another kind of pinky purpley here. So black is definitely a mixture of dyes. So that means both our green and black inks are mixtures of dyes, and we can tell that from the fact that they produce more than one spot. So one spot means the substance is pure, it's not made up of multiple substances. If we have multiple spots, any more than one spot, that means that it's a mixture of dyes. So the first bit of analysis that we can do from a chromatogram is looking to see whether our substances are pure substances or are a mixture of components. The other thing that we can do is look at the distance travelled by each of the spots in the chromatogram and work out the RF value of each of the components within our substances. So what we'll do is we'll do this for the blue and for the yellow spot. Obviously with the black ink, there are other colours and we can calculate the RF value essentially of all of those components, all of the individual dyes within that ink. But we'll just do it for the yellow and the blue now. So this is why it's important to mark your solvent front, because the RF value is a measure of how far our spot or our substance has travelled by comparison to the distance moved by the solvent. So we need to measure first of all the distance moved by the solvent, and that is the difference between the baseline and the solvent front. So that's the distance that I've marked on the diagram now, the distance between the baseline and the solvent front, because remember our spots have only moved from that baseline, they haven't moved from the bottom of the chromatography paper, so just be careful. Sometimes in the exams they mark these distances on, but they'll maybe mark the distance from the very bottom of the chromatography paper as well, just to throw you off. So be careful that you use the distance between the baseline and the solvent front. So that's the distance moved by the solvent, and I have measured that on the actual chromatogram to be 7.5 centimetres. Obviously it might be a wee bit different on your screens depending on what size of screen you're watching this on, but that was 7.5 centimetres. We then need to do the same for each of our spots to work out how far our substance has travelled up the chromatography paper. So if we have a look at the yellow here, Remember, we want to see sort of where it's most condensed and the centre of that spot. Generally in the newer papers, they kind of mark these distances on for you. So what we would then need to do is draw a line down to the baseline. So remember, we want to work out the distance travelled by the spot or the substance, and so it starts on the baseline and then moves up to this point. So remember, it's the distance between the baseline and not the bottom of the chromatography paper. I've worked that out in real life to be 5.5 centimetres, and then the RF value is just a very simple calculation. So for the yellow, it's going to be the distance moved by the substance, that's our 5.5 centimetres, divided by the distance moved by the solvent, that's our 7.5 centimetres. Put that into your calculator. So that comes out as 0.73 reoccurring, but normally that's rounded off to either 1 or 2 decimal places. Just read the question carefully. And notice how it doesn't have any units, because these units of centimetres just cancel out. So it's written as a decimal and with no units. And do remember that if you've done this correctly, your RF value should be less than 1, because your spot or your substance will have travelled less distance than your solvent. So the distance travelled by the solvent will always be greater than the distance travelled by the spot. Let's do that really quickly for the blue one as well. So again, you measure the distance from the baseline to the centre of the spot, just a vertical line drawn up. And in this case, I found the distance travelled by the blue spot to be 5.9 centimetres. So the calculation is RF equals distance moved by the substance, that's our 5.9 centimetres, divided by the distance moved by the solvent, that's 7.5 centimetres. And that comes out as 0.79 to 2 decimal places. So you can see that the blue has a higher RF value than the yellow dye, and that just simply means that the blue is more soluble in the solvent, whereas the yellow spot is more attracted to the chromatography paper, the stationary phase. So the yellow is more attracted to the stationary phase, the paper, and the blue is more attracted to the mobile phase, and that will be our solvent. So that is how you calculate RF values, and you should get a little bit of practice of that from other questions. So that's the separating technique of chromatography, and all that's left to say is that you should try this experiment at home yourself, just so that you can see how it works and get practice in actually doing this method. So this is an experiment that you very much can do at home yourself, just with safe materials like water as a solvent and felt tip pens. So follow the method that I used in this video, or the method that's in your notes. And you could even then stick your chromatogram into your notes, and you could work out the RF values of different dyes within the inks in your felt tip pens. One small note, highlighters don't seem to work that well, so if you can get felt tip pens, and remember to draw your baseline and your solvent front in pencil. Enjoy!